A gamma invariant probability measure. So this is an abbreviation for invariant random subgroup.
So I guess invariant subgroup is normal.
No, it's not a subgroup even.
Oh no, I mean the reason for this is why you go IRS.
I mean because I'm just randomly picking a subgroup and then asking like what group elements are there. That's pretty good. Now what is an example of it? Some examples. First, trivial example is to look at normal subgroups and look at the delta major at there. Because this normal subgroup is invariant with respect to the conjugation, this is an invariant probability measure. Now here is a more, so let's say that Xm is a probability measure preserving space. So in the sense that the action of my group here preserves the measure. So now what I can do is I can define the stabilizer map from Xm to sub gamma. So what I do is to each x I assign the corresponding fixed nodes. So gamma x here is all those g in gamma such that gx is x. These are fixed points. And moreover, this assignment is gamma equivariant in the sense that star of g dot x is exactly going to be g gamma x g inverse, which is the action that I have on the other side. And of course, it is a measurable map and equivariant with respect to the action. So what I can do is I can push forward this measure in here via this map to get an invariant probability measure on sub gamma. So star m is an IRS. So this is something that is very general in the dynamical system, that we can push forward measures, and the equivariance gives us invariant measures under the equivariant map gives us invariant measures here, and then therefore this is an invariant probability measure. Moreover, there is a theorem of Abbott, Glasner and Lederle, which says that this is the only way to produce IRSs. So, given an IRS mu, which is an IRS gamma, there exists a probability measure preserving gamma space Xn such that mu is exactly the push forward of m under the stabilizer map. So basically this exhausts all possible IRSs that there are. So there are no other IRSs than this stabilizer map.
I have a question.
Yeah.
Can you clarify the relation between Chabauty topology and the Virtuous topology? I consider, as you said, consider subgroups as collections of these vectors of zero vectors. Because one thing that confuses me is the closeness question, right? It's not clear.
What do you mean by closeness?
So these collections of elements in subgroups, they are not necessarily closed, right? If I consider the closed subsets of 0, 1 to the gamma.
What? I mean, I'm just saying that this is somehow sitting inside 0, 1 to the power gamma, so this may not be all the things inside there. So I don't think the closeness problem arises here.
No, I'm not saying this is problematic. I'm just saying that there is another natural topology that seems very related, which is, the so-called Vectorist topology. You consider 0, 1 to the gamma. You consider closed subsets of it.
Maybe they agree, I think. Probably these two topologies agree on these things.
But if I take a subgroup and represent it in this form, is it a closed subset of 0, 1 to the gamma?
I think so.
Yes, what?
Sorry, what is the question?
Because this topology is related to you consider each subgroup as just as a collection of elements in 0, 1 to the, and then you have there is a natural topology called the Vectorist topology on closed subsets. But now I'm not sure that if you take a
When you take a limit, you should be able to say that it is.
No, if it's like legal elements. But okay, if this is off topic, maybe we should.
Yeah, I mean, yeah, I think probably.
I just thought maybe this is no.
I don't know. Maybe this is this. I believe that these two topologies should agree on sub gamma. So I think that because on the collection of closed subsets there is a one unique topology because of the result of FROS. That makes it that is nice. So I think this topology. Okay. Anyways. Okay. So what I want to do now is to define an amenable group maybe. So gamma is again a discrete group, and I look at L infinity gamma. So these are all maps from gamma to C, such that the supremum is bounded. Now there is a nice action of my group gamma here. This is of course the left translation. So S dot F E is just the left translation. So I'm translating L infinity gamma from the left hand side by the action. So gamma is called amenable. If there exists a positive bounded linear functional phi from L infinity gamma to C such that phi of S dot F same as here. This must be for every group element and every element in A infinity gamma. So this is what is so this phi is sometimes called a mean. So there is a gamma invariant mean on L infinity gamma. And of course examples are solvable groups. Some non-example solve the free group on any generators and in So this is of course a well-known theorem which says that the collection of amenable subgroups is closed in the Chabauty topology. And one other fact there is something called an amenable radical. So this is the largest normal amenable subgroup. So given a group, we can always find there's a unique largest normal amenable subgroup that sits inside it, and this is what is called the amenable radical. So existence of it is pretty much like Jones' lemma argument, that there is a maximal subgroup there and this must be unique. Okay, so now this theorem of Margulis, this is a special case of Margulis' normal subgroup theorem.
Wait, the largest normal in what sense of inclusion?
Yeah.
Okay.
So in the sense that this is, let me call it rad of gamma. So this just means that every normal amenable subgroup is contained inside amenable radical. Okay, so maybe I state the Margulis normal subgroup theorem before I say a few words about it. So this is a special case of it. So let's take gamma to be epsilon g in bigger than or equal to 3. Then Margulis showed that every normal subgroup inside the group is either contained in the center, hence finite, or has finite index. So what Glasner and Lederle they wanted to do was to go beyond normal subgroups. So they wanted to ask if they could prove some such result for some subgroups that are not necessarily normal but encompasses all normal subgroups. And that is how they introduced this notion of Boomerang subgroup. So a subgroup H in the collection of is called Boomerang. If given any non-group element, we can find the sequence, increasing sequence, such that g to the power ni h g minus ni converges to h in the Chabauty topology. So, in other words, this is basically saying that H is a recurrent point with respect to the group action for every G in my group.
Reminds rotation.
Sorry?
Reminds rotation.
So it's basically saying that in the orbit I will always come back to H even if I keep on conjugating. Now, of course, an example. Trivial example, normal subgroups for trivial reasons, finite index subgroups are also going to be Boomerang. Now here is a non-trivial, I mean of course not non-trivial but a more, can I write here? Yeah. Okay, so here is the third example. So I claim that every invariant random subgroup is supported on Boomerang subgroups. So if there is an invariant probability measure on sub gamma, then mu almost every h is actually Boomerang. So this is what I claim. And the reason is Poincare recurrence theorem. So Poincare recurrence theorem tells us that if, okay, so maybe state here, This is concatenate. So it says the following. So T from x to xm to xm is a measure preserving transformation, and m is a finite measure on x. X is some measurable space. Then m almost every x in x is recurrent with respect to t. So which is basically saying that so what this means is that if I pick a neighborhood u containing x, I can find some n naught in m such that t n naught of x is again in this u. So now let's pick mu to be an IRS, and I fix this G in my blue gamma, and I look at the corresponding TG map from sub gamma to sub gamma, which sends H to GH G inverse. Now this TG, let's do the mu's here as well. Now since mu is an invariant probability measure, TG is, this is a measure preserving transformation. So by concurrent recurrence theorem, I can find a co-null set. We call it UG, such that every H in UZ is recurrent with respect to this map TG. Okay, so here I assume gamma to be countable. And now what I can do is I can look at the intersection of these uses. And then every H in this intersection is going to be recurrent for every element. And of course, this is a cone also.
But you claim something about the support.
Yeah, that's exactly what do you mean by support.
Support is always a closed set. But maybe you use another, maybe you didn't mean that.
Another
section of measures of
this is
sets of full measure.
Yes, but we use when we say support.
The closure, yeah, you're right. No, it's really about almost there.
This is maybe not your terminology, but many people when they say support, they mean close, not a common. And you use topological support. Okay.
okay.
So I think he means that almost every point is equal.
Yeah, that's it.
Yeah.
Okay, so this does the job for me. So now with all this, what they proved, yeah, I can. So this is the theorem. They of course wrote many other things. So they showed that if you take gamma to be a ln G, n bigger than or equal to 3, then every Boomerang subgroup is either contained in the center, hence finite, or has finite index. and this generalizes the result of Margulis.
Is there an example of a boomerang which is not normal definite index?
Yeah, I mean every IRS. If you take a non-trivial IRS, then this should work. Okay. So
do you know if commensurate subgroups
I think so. I mean, I think they have it on internet, but maybe I don't
I
really.
think this was an open question. Rules regarding if commensurate subgroup have this probability that
I don't really know. I mean, okay. So, where we came into the picture because we somehow come from the others. We wanted to enlarge the point of view. So this is where the story, second part of the story comes in. So we wanted to enlarge the collection of all subgroups and somehow put them in a bigger object in a nicer way, and then study those objects in order to find maybe some new things. Okay, so now given I have again gamma, which is a countable discrete group, and then L2 of gamma. So this is all square soluble functions from my group to C. Now what we have is the left regular representation of my group gamma. Side B of L2 gamma. So B of L2 gamma maybe right here. So this is all linear bounded maps. So what it does, so this is the unitary representation. What it does is that it just translates everything from the left. So S is in my group, J is in L2 gamma, and T is again in my group. So if I do in terms of an orthonormal basis, what it does is that lambda S of delta T is just delta S. I'm just translating every orthonormal basis, and this is how this unitary operator is defined. So now what I can do is I can look at the span of these lambda S's, which basically forms a group ring, and then I want to close it. I will close it in the weak operator topology, and the object that I get here, this is what is called the group von Neumann algebra. Group von Neumann algebra. And just to recall, the weak operator topology, so Tn converges to T in the weak operator topology if and only if T and the inner products converge. Okay, so now what we can do now is to look at the collection of all subalgebras of L gamma. So when I say subalgebras, I mean von Neumann subalgebras. So this is all those M is a von Neumann subalgebra of L gamma. So much like looking at the collection of all subgroups, we now look at the collection of all fundamental subalgebras. And there is a nice topology on it that makes it, it's not ever going to be compact, but that makes it Polish and second countable and metrizable. So this is what is known as Efros-Maréchal topology. So before I introduce the topology, maybe I say a few general words about so where the topology, the motivation comes from. So this is a definition by Frost from 1970s. So let A be a compact Hausdorff space, and let E alpha be a net of closed sets, subsets of K. And for any element x in K, let Wx denote the collection of open sets containing X. So now what we can do is we can define limit of this net E alpha, which is now the collection of all closed sets, to be all those elements in K such that for every open neighborhood containing X, U intersection E alpha is non-empty eventually. So there's some point after which the intersection becomes non-empty, and then we can define lim sup to be all those elements in K such that for every open neighborhood containing X, U intersection E alpha is non-empty infinity of it.
Question, so when you say a net of closed subsets, is it all subsets?
No, just any net of closed sets. So given a net of closed sets, we can define this lim for lim sup.
And when you say net, it means a collection just given one set inside another?
No,
No,
just any connection.
So they don't get to reward.
No, there's no relationship between E alpha and
I see.
So this is a theorem of Efros, again from the same paper, 1970s, where it shows the following. There is a unique topology on Fk. So Fk is the collection of all closed subsets of K. So this is the collection of all closed subsets of K. This is called the convergence topology. And this topology is exactly given by E alpha converges to E if and only if lim E alpha is same as E is same as the lim sup.
Do you know if it agrees in the case of a metric space with the Gromov?
It agrees with the Gromov topology. So now So now with this, because so there is something from the von Neumann algebra theory which says that the von Neumann.
Sorry,
Yeah.
question. So for in this theorem now you have specific net, right? You have one set after another. It is contained in this sense.
What do you mean?
Well,
So I'm just saying, given any net, we can define as name infinite name soup. And then I'm just saying that the topology is given exactly by this.
I see. So it's kind of definition.
Yeah, this is yeah.
So the Thomas topology generalizes the formal household topology in the non-generalizable case.
I think so. I think they all agree. So here is one fact that so if M is a von Neumann algebra, so if M is a von Neumann algebra, then the ball of M is compact in the weak operator topology. The unit ball. So now, to define the Efros-Marisan topology, there is one natural way of doing it. So I will say that if M alpha and M, these are von Neumann subalgebras of my group von Neumann algebra, M alpha converges to M in the Efros-Marisan topology if and only if the ball of M alpha converges to the ball of M in the convergence topology.
So here, the topology is which operator topology is what you do.
Sorry.
I mean, in order to define this topology, you need the notion of open sets, right? You the green inference, so on. And the open sets are the weak operator topology.
Yeah. They're all
the restriction to the
yeah,
ball of,
yeah.
okay. I see.
I mean, once I have the convergence, everything, the open sets are basically the complement of the closed sets, right?
Do you know if this is metrizable, in case you have the metrizable?
Who is one? The first Marisan topology is a metrizable, the second countable.
Okay, this is metrizable.
Sorry, I'm so confused
Yeah.
about the question I
Yeah.
asked before. So in this theorem, to define this topology, you need a net of closed sets, right?
I mean, in FK there are only closed sets because FK is the collection of all closed sets, and I'm saying that on this FK there is a unique topology, and this topology is given by this.
But to have this defined, to have defined lim-inf, lim-sup, you need a net of closed subsets, right?
Yeah.
So what exactly is your net closed subsets?
What do you mean by? No, I'm just saying that the once I
For any?
yeah for any.
So for any.
Yeah, so I mean once I give you what is like the convergence things, then everything the topology is defined by that, and that's exactly what I'm doing.
And in the Efros-Marisan topology, is it also for any?
Yeah, it is for any, right? I mean, given any M alpha and M inside L gamma, I see M alpha converges to M in the Efros-Marisan topology, the balls converge in the convergence topology. This is general. Okay. I mean, of course, there is a von Neumann algebraic definition of it. So, what I can do is I can define lim-inf of E alpha. So this is all those elements in L gamma such that there exists some x alpha in M alpha such that x alpha converges to x in SO star, SOT star topology or star SOT, and then we have lim sup to be all those elements here such that you can find m alpha such that x alpha converges to x in weak operator topology. And then I say that, oh, this is m alpha. Sorry. Then we say that m alpha converges to m in the across Margulis topology if and only if the lim is same as m is same as the lim sup. Here I have to look at the formula of the relative. This is more the operator, like the formula of the perspective. I mean, in between, so there is a theorem of Franz and Margulis, which says the following. Sorry, this is Heidelberg. Slope. So it says that, so this is true for infinite volume algebras, but I will stick to L gamma. So m alpha, m, these are volume and subalgebras of L gamma. So we know that there is a conditional expectation for each of them, right? The trace preserving ones.
ICC.
Sorry?
Need ICC maybe or not?
No, I don't need ICC. I mean, for every finite volume algebra, there is a every subalgebra is
You're
a
randomly fact. Yeah, good.
So there is a conditional expectation for each of them. So m alpha converges to m in the across Margulis topology if and only if E alpha of x converges to E of x in star SOT for all x in L gamma. So this means that when I project them by these conditional expectations, they converge in star SOT to the corresponding conditional expectation there. So just to briefly say what these are, these are basically linear projections. So there is some from theory of volume algebras. What we know is that every subalgebra is in the image of a conditional expectation. What we call these are linear projections. So what their theorem says is that in the first Margulis topology, if I project them by the corresponding linear projections, then the projections align nicely. That's what the theorem says. Then this is another interpretation of the first Margulis topology. Okay, so we have read this piece. So, okay, so the first theorem that we proved with Yair and Hannah is that if we look at the map, let me call it L, from sub gamma to subalgebras of L gamma, that sends every subgroup here to the corresponding group on Neumann algebra. This is continuous. And here I have the Chabauty topology. And here I have the across Margulis topology. Yeah.
So have something independent on any collection M alpha. On the right, you need some.
No, the right is also independent of it, right? I mean, it doesn't matter what connection I choose. I mean, the right is, I mean, this is just a way to make sense of the topology, right? It is easier for me to define in the terms of data.
But you need to structure of a net, some particular structure of a net?
No, I don't need anything. I mean, I'm just saying that if Hn, all I'm saying is that if Hn converges to H here in the Chabauty topology, then L of Hn converges to L of H in the F-Marissa topology. The definition, I mean, I'm just defining it in terms of net, but these are no particular nets, right? I mean, the topology is defined by the convergence of the nets, right? That's all I'm using.
Are you sure you don't need any assumption on gamma?
No, gamma is countable.
So I mean, the phenomenon algebras of subgroups are closed, they close subset.
Yeah, so what?
Are you sure?
Yeah, so what is the problem?
I mean, if you take, for example, the copy of Z inside your group.
I'm not saying that this is onto. I'm just saying it is continuous.
Yeah, but the image is closed, right?
Yeah, so what happened? What is there? What, I mean, the image can be closed, but there is no problem with that.
It's strange, because for example, if you take Z as a subgroup, and then every other diffuse phenomenon algebra is a limit of commutation by union.
I don't see any obstruction to it.
Yeah, no, I'm not saying it. It's a very strong statement. Okay.
So what this tells us is that we can view sub gamma inside subalgebras of L gamma. So subalgebras of L gamma is like a very nice big container for these sub gammas, and these sub gammas are sitting continuously in there. So if we study the subalgebras of L gamma, then we can study the subgroups in particular, and that's exactly where we wanted to study the subalgebras of L gamma. So again, following the procedure, so we can now define invariant random algebra. So an invariant random algebra, let me abbreviate it as IRA. An IRA is a gamma invariant probability measure on subalgebras of L gamma. For an IRA. When I say gamma invariant, there is a nice action of my group on subalgebras of L gamma. So this is again the conjugation action. And then this assignment that we did, this is a gamma equivariant map, in the sense that L of GH G inverse is exactly L of GH G inverse. So an example, if I want, let me give some examples here. So again, I can look at delta measures on M, and M inside L gamma is a gamma invariant subalgebra. Then this is an example of an IRA. And the second thing I can do is I can take an IRS and push it forward via this map L to get an IRA.
claim that's all the ways you can get it?
For some groups, yes. Not all the time. So for some groups, this is what we want to show.
But you also have examples that.
Yeah, there are examples where not every IRA comes from IRSs, for sure. So I have 25 more minutes. How long do I have?
40.
40?
Yes. But yeah,
Good.
if this is too much, you can stop earlier.
Okay, so what we wanted to do first of all was to understand these IRAs. Like if we could understand where these IRAs came from. So we started off. So what was done to start off with these delta measures? So if I pick a delta measure, which is now an invariant subalgebra, and we wanted to understand if we could completely describe it. So basically the question comes from the following. So maybe I say, so M in L gamma is gamma invariant. This just means that lambda G M lambda G star is again M for every group element. So when I conjugate it, this is like a non-commutative normal subgroup theorem, something like that. Non-commutative version of normal subgroups. That when I do the conjugation, I land up back in M again. So an example of such a thing is M is when it is coming from a normal subgroup. So if I come from a normal subgroup, I conjugate them, I go back inside the normal subgroup again. So the question that people asked in the beginning was, are there examples of groups for which every gamma invariant subalgebra M inside the group one Neumann algebra is of the form L of N for some normal subgroup. So in particular, all these delta measures, they are coming from IRSs for these groups, if such a question has a positive answer. And this is a theorem which says that gamma is SLNG n bigger than or equal to 3, and assume that the center of gamma is trivial. Then every delta M, where M is a gamma invariant subalgebra, maybe I should here. Then every gamma invariant subalgebra inside L gamma is of the form L of N for some normals. So in particular for SLNG, the delta IRS are all coming from IRSs. So this is what we showed. So, motivated by this, so because these are higher rank groups, we wanted to understand if there are other groups for which these delta IRAs are going to come from IRSs, and that led us to define what we call the invariant subalgebra rigidity property. So gamma has, let me abbreviate it as ISR, if every gamma invariant subalgebra inside the group on your algebra is of the form L of n or some normal solution. So in particular, every delta IRA comes from a normal subgroup. And then we showed that if gamma is a torsion-free hyperbolic group, with trivial, I mean, radical, or even a finite product of subgroups, then gamma has ISR property. So in particular, for these groups we understand these delta measures, the delta IRs. So of course, what we wanted to do was to say if we could do something for modes like something bigger than the delta IRs, if we pick an IRA, can we say in general that if it comes from some IRS or something? And motivated by the notion of Boomerang, of Glasner and Lederle, so we introduced the notion of Boomerang subalgebra. So M inside the group von Neumann algebra is called Boomerang. If for every G in my group I can find some increasing sequence of natural numbers such that lambda G to the ni m G minus ni converges to m in the IRSs topology. So this is basically saying that this subalgebra M is a recurrent point for every group element.
Is it different if you take a unitary integer?
I mean, this could be very big. I don't know what an example of such a boomerang would be.
So it's a different concept?
What do you mean?
Instead of requiring the G's in gamma, you take a unitary error gamma.
I mean, you mean the definition would still make sense. I just do not know of an example.
You don't know if it's a different concept.
I do not know of an example that satisfies this property that you are saying.
I mean, they will be the same.
What do you mean?
I mean, the definition you require, if for every...
Yeah, I'm not talking about the definition. I'm just saying that I do not know of an example that satisfies an unitary that doesn't come from the group elements. I just do not know the Boomerang subalgebra.
You don't know an example of a unitary that is not in the parent.
No, I'm saying that, so in your definition, what is an example of the Boomerang subalgebra?
I mean...
No, what is an example? I understand the definition. What is an example?
no, I was just wondering...
No, I mean you can do it, but I mean this could be like, it could be that this M could be very like trivial, you can see. I mean, an example, I mean, this because this is a very stringent condition. Okay, so one example. So for example, one is when M is a gamma invariant subalgebra. This is of course trivially satisfied. Now second, because of again by concurrent recurrence theorem that is there on this board, every IRA is supported on Boomerang subalgebras. And this is exactly by concurrent recurrence theorem, because concurrent recurrence theorem doesn't need compactness or anything. As long as my measure is finite, I can still use it to get recurrent points. So in order to answer this question for general IRS, what we needed to do was to understand what Boomerang subalgebras are. Like if there are groups for which Boomerang subalgebras necessarily come from subgroups. And that's exactly what we showed. So theorem. So take gamma to be a torsion free hyperbolic group with amenable radical again trivial. Then every Boomerang subalgebra M inside L gamma is of the form L of H for some subgroup. In particular, all these Boomerang subalgebras, they come from subgroups. So as a corollary, because of concurrent recurrence theorem, it follows that if gamma is a torsion-free hyperbolic group with trivial amenable radical, then and mu is an IRA, then mu almost every M is of the form L of H for some subgroup. So in particular for these groups, if I pick an IRA, then they necessarily come by the push forward of these IRSs.
So does this theorem also say, no, that's for the hyperbolic groups, but before even the theorem about passing from the groups to the polynomial subalgebras, it gives the range. But
the range is never on 2, but it says that the range is on 2 if I restrict to Boomerang.
yes, so the range is the Boomerang.
Yeah.
I guess here you use the fact that you have these hyperbolic groups.
Yeah.
Do you expect these to be in general?
We do. I mean, for sure, this is not true in general, but this could very well be true for groups with trivial amenable radical per se.
What is the relevance of the reality of the amenability?
Okay, so what is the relevance? So what we know is that so somehow amenability messes up with this. This brings me back to, if you recall, in the beginning we discussed that if gamma is a discrete group, and then RA of gamma is the largest amenable normal subgroup. So now what we can do is we can in the group from the von Neumann algebraic perspective, so to gamma we assign this von Neumann algebraic object L gamma, the corresponding group von Neumann algebra. Now to the amenable radical we can also assign the corresponding group von Neumann algebra associated to it. So now we know that this is largest here, sitting inside here. This is largest in the largest in normal amenable subgroup. Now, can we ask if this is the largest amenable in a sense of von Neumann algebras which are invariant? And the answer to that question is yes. So this is a theorem that we proved. Guy and Hana. That the group von Neumann algebra, the amenable radical, is the largest gamma invariant amenable subalgebra of the group von Neumann algebra. So if the amenable radical is not trivial, then there is some amenable subalgebra there. And somehow this messes up with these properties that are there. Like we know that this cannot come from, you can find a subalgebra that doesn't necessarily come from a subgroup. And this is somehow difficult for us to handle. Yeah.
Also, can you choose age pretty much to be a boomerang?
Yeah, so L of x is boomerang if and only if h is boomerang.
How many boomerang pre-merges can you have?
Pre-merge, what do you mean by
like how many? Is it injective?
Yeah, this is. I mean, there's only one way of. There's one way of choosing it. So I would stop here.
Just to get a feel for the proof, so I'm asking, I guess this was in the introduction that you mentioned this result by Glasner and somebody else.
Yeah, about Glasner, yes.
We generalize this Margulis.
So this is Glasner and Lederle, sorry.
If you compare the proofs, is it like completely different?
Yeah, it's completely different.
Okay.
Yeah, because they do some sort of an. I mean, I don't know the proofs by my head, but they do. There's different analysis.
And also the amenable radical isn't necessarily the same.
Yeah.
So, at first, for the sake of generality, but I don't know if it's interesting to share. I mean, probably you could also go to sister algebras.
Yeah, the problem is that.
I saw a problem that something doesn't work.
I mean, even before going to.
How do you find the first topology?
Even before there, if we can ask for the invariant subalgebras. Like you can pick, let's say, the reduced group sister algebra, the free group, and we pick an invariant subalgebra. Does it come from a normal subgroup? And the problem with our techniques is that there is no reason to expect that there is a conditional expectation back onto it. So our techniques cannot be applied.
Well, you have this pseudo expectation.
It will not work.
It will not work.
But also in the first topology, I mean, you're using the fact that it's a von Neumann algebra gamma?
Yeah.
So that it has the weak start.
And also the ball is weak operator topology compact. In the C algebra, the balls are not going to be compact at all. So there's a big problem there.
Good choice then for von Neumann algebras.
We have concrete examples in which your statement, groups for which the statements would not be true. So,
Yeah, like the lamplighter group.
Sorry?
Lamplighter groups. So. So even we don't need to go for Boomerang even. We can find an invariant one that doesn't necessarily come from an anomalous opening.
Oh, right. So it's
So it's a surface entity.
Yes. But there are no examples for which so your statement isn't true, but still this weaker property proves that
The invariant subalgebra ISR property,
yes.
we do not know from nature.
So it will be the same.
Yeah.
So it's possible that it's the same.
It's possible. It is possible that for groups with trivial amenable radical, these things are very rigid, but we do not know.
Any other questions? Online audience, maybe?
There's some question in the chat, maybe, I think.
No questions. Okay. Thank you for watching again.
See you later. This is there. That's how to, it's not.